So, yesterday we talked about what equilibrium is. All right, it's when the rate of the reverse equals the rate of the forward reaction. What we're going to start doing over the next couple of days is looking at is the equilibrium shifted more towards the left or the products, or the left or the reactants, or the right and the products, or is it somewhere in the middle? And then we're going to learn how to shift it one way or the other depending on what we want to do. Okay, and then we'll get into the math behind it, which will allow us to calculate concentrations and determine how to shift it and how much to shift it, et cetera, et cetera, et cetera. But the first thing here is the position of equilibrium. Guys, the position of equilibrium, okay? So a general equation for equilibrium, just a blank, no actual chemicals, is we would just say, whoa, can't write in weight, on weight. Oh my gosh. And my pen doesn't work. There we go. Okay, reactants going to products. So you're used to seeing just an arrow here, right? Going in one direction. But we've now talked about how the reaction goes in both directions at the same time. So these are half arrows that denote equilibrium. The other way you can do it is you can literally do a double-sided arrow. You'll see that. I'm usually going to draw this. So. Okay. So we have reactants going to products. All right. If you have mostly products, your reaction is pushed in this direction, and we're going to talk about later on what pushes the reaction in a certain direction. And it's mostly products and not a lot of reactants. We say the equilibrium is to the right. Or it's been shifted to the right. That means there's more products than reactants. Okay? So if you have the equation, oxygen gas, 3 molecules of oxygen gas can decompose into 2 molecules of ozone. Okay? Which way do you think this reaction is shifted mostly at room temperature? Do we have more oxygen or do we have more ozone in this room? So it would be shifted to the, there you go. Okay, so this equilibrium is shifted left. In fact, you would say it's probably far to the left. Okay. All right, now you can push the reaction in certain directions. Okay, so if we dissolve, we go back to our dissolving a product in water. So we're going to take sugar, we'll dissolve it in water at 20 degrees, so basically room temperature. You reach the saturation point, which we will say is this one. Room temp. So it saturates, you're at equilibrium. You know you're at equilibrium because the concentration is constant. If you increase the temperature, right? Now, most things, not everything, but most things will dissolve better and hotter in a warmer solution. So we start to increase again. So it's 30 degrees. So room temp, we increase the temperature to 30 degrees. In this period, you get the reaction going. It's pushing more to the right. And then it reaches another equilibrium at 30 degrees. Okay? In which case we have a higher concentration of sugar. Then you can do it again. You raise the temperature another 10 degrees. And you get a new equilibrium setting in. Each one of these has a higher concentration of sugar. So the temperature will impact the equilibrium position. Okay, and that's going to depend, which way it goes is going to depend if it's an exo or endothermic reaction. Okay, so temperature will affect the position of your equilibrium, whether it's to the right or to the left. Okay, can I flip the page? Or scroll to the next page? Okay, what about concentration? Does concentration change the equilibrium position? So, if you have NO2 and N2O4, if initially I put N2O4 into a beaker, all right, seal the beaker, we're at 100 degrees Celsius. This is all I have at the beginning. It's going to decompose until it reaches equilibrium. Okay. If you look at this, the N2O4, this is concentration here, will decrease, and then it levels off. It decreased by 0.2, what is it? I'll just say molar, 0.2 molar. Okay, we went from concentration of 1.0, the initial, to 0.8, so we went down by 0.2 molar. What happened to the concentration of NO2? Just look at the graph. What happened? It goes up. It goes up by? It goes up from 0 to 0.4. Why did it go to 0.4? Not quite. Yeah. One molecule of this produces 2 molecules of this. So if this goes down by 0.2, this has to increase by 0.4. Let's put an arrow up. Increase by 0.4 molar. Okay. So that was where we ended up. We started with 1 molar of N2O4, and we finished at equilibrium 0.8 molar of N2O4 and 0.4 molar of NO2. What if we flip it? Same temperature, except we put 2 moles, or 2 molar, concentration of 2 molar, of NO2 in there. So now we're starting with the NO2. This one over on the left. So we're going to decompose this way. If you let it run, this is what you get. You finish with how much NO2? 0.4, and up here was 0.4. And then the N2O4, because it's increasing, increased to 0.8. Same concentration as above. Okay. Now, what can you conclude about the initial concentration of reactants or products? Does it have an effect on the equilibrium? It does not. You end up in the same spot. Okay? So, what will the initial concentration change? It won't change your final position, but what will it change? It changes one specific thing that we studied in the previous chapter. It'll change how fast you get there. Okay? Because if you have more of something, you have more collisions, the rate is increased. Where you end up is the same. So it doesn't impact the equilibrium position. but the rate is changed or affected, whatever you want to say. Okay. And I just want to note, they had to, what would happen if I changed the temperature? These are at the same temperature. Why is it important they're at the same temperature? Because temperature does change the equilibrium, right? Which is what this thing says. Temperature will shift the equilibrium. Okay? So if you're going to perform an experiment like this, you have to be at the same temperature. Okay. What does a catalyst do, peoples? This is the last chapter. Increases the rate. Is it going to change what the ratio of products is going to be? No, a catalyst only ever affects the rate. That's all it does in anything. Okay? It's a definition. So if you look at the graph, with no catalyst, it just takes longer. Your time is here. With a catalyst, the rate changes and you get there a lot faster. That's it. But the final position is the same. So a catalyst does not have no effect on equilibrium. No impact on Jut. Only change the rate. How fast you get there is the only thing it will change. All right? Temperature will change the position. Initial concentrations have no effect, just it'll change the rate, and a catalyst will only ever change the rate. Because that's the definition. Okay? 3 things. Please answer those questions. And we'll go over the questions. I'll give you like 10, 15 minutes, and then we'll do the next one, which is enthalpy and entropy, which is